Welcome to this new in-depth analysis. Today we're diving into a fascinating area, very timely, I'd say, using deep learning, so advanced artificial intelligence, to guide investment decisions. Something that we have already talked about in the previous video, so we want to dig a bit deeper into how reliability is tested. We talk about sensitivity analysis, stress tests, and simulations. We are talking about millions of parameters, but they work like black boxes. Understanding the why, the internal logic path, isn't always easy. So trust can't come only from the past, from its worked well so far. We need to understand whether they are robust, whether they can withstand storms or never before seen conditions. These tests precisely serve to build then that trust. Perfect, so let's start from the model. It's a wide scope, it invests in many different ETFs, US equities, European equities, emerging markets, but also specific sectors. And the goal is to beat the benchmark, the S&P 500. Non-US ETFs provide advantages compared to a US-only model. And how does it decide which information to use? So basically the model, the preprocessing, it's similar to the model presented in the previous video. The features are calculating, extracting price volatility, benchmark volatility, calculating classic technical indicators like RSI, MACD, the ones that help understand momentum and whether a security is overbought. Then we have sentiment indicators, macro variables, growth, inflations, and seasonal signals. So all these data are normalized, put into sequence, and prepared for the neural network. The architecture presents several layers, so we have the LSTM layer, and then convolutional or attention-based elements that are able to capture complexity and catch better nonlinear relationships among the various inputs. But perhaps the most interesting thing is the loss function, what the model learns to do. Not just predicting prices, so it's trained specifically to maximize the Sharpe ratio, the returns, versus the benchmark, in this case the S&P 500. And how do they make sure it doesn't peak into the future? A classic risk with historical data. So we use a rigorous method called walk forward, like a window that slides over historical data. Imagine this window. So inside we split the data into training, validation, and testing. We train, optimize, and then test on data that the model has never seen. Then you move the window forward and we repeat the process. Good. Before we jump into the stress test, a quick look at the historical backtest results. So we have that the model portfolio posted a compound annual growth rate of 26.8% compared to the benchmark over the same period with a return of 10.5%. Quite a difference, but returns aren't everything. How did the risk look? The Sharpe ratio, which measures return per unit of risk, is 0.06 for a portfolio versus the 0.03 for the benchmark. So even adjusting for risk, performance was superior. But if you want to go deeper, we also have to consider the max drawdown, the maximum loss from a peak. That was 54.8% for a portfolio and 60.6% of the benchmark over the same period. This tells us that to achieve that extra return, there were in any case phases of considerable volatility. And looking at more recent data, the last year, the results are even more pronounced. 46% of compound annual growth rate for the portfolio versus the 22.5% for the benchmark, a Sharpe of 0.13 versus 0.05 of the S&P 500. And here, the risk management in the last year seems very good. A max drawdown of only 11%, that was much less than the S&P 500 of 15.6%. So, summary in the backtest, historically the model beat the index, sometimes by a lot, but the historical drawdown reminds us it wasn't a walk in the park. The past looked good, but how would it react if the future were different? And that's where stress tests come in. Exactly, with a system this complex, nearly 1 million parameter, and not entirely transparent, we can't stop at the backtest. We must actively simulate alternative future scenarios, and here we want to describe two main methods used for these tests. Let's look at the first, replication of historical patterns. Take a tough historical period like the financial crisis of 2008, or a strong rally such as the period from 2012 to 2014, and use the daily returns from that period to create a simulated future, as if history were to repeat, kind of like replaying the same movie to the model starting from today. That's the concept. So technically, you take the daily percentage changes of ETFs, the benchmark, and the VIX from that period and apply them to today's price cyclically. The advantage is the following: you preserve the exact correlation structure and the sequence of shocks as they were. It's, I would say, a test of coherence. How would you react to a real past context but applied today? But then we have the limits, and history never repeats exactly. The second method is the generation of correlated synthetic returns. The idea here is different. Instead of copying the past, you generate new never-seen data that statistically resemble the past. That is, you generate random daily returns that have the same historical mean and, above all, the same historical correlation among assets. And how do you do that in math terms, without diving too deep into linear algebra? In practice, you estimate the historical mean and covariance of returns. Then, depending on the scenario, optimistic, pessimistic, high volatility, you can tweak those parameters a bit. So we have the drift for the alpha, volatility as the beta, and at that point you generate random numbers from a normal distribution, and with a mathematical transformation like Echolensky decomposition, you transform them into daily returns with the desired mean and correlation. The limitation here seems to me that we have more flexibility, but perhaps less real-world grounding. The advantage is that you explore sensitivity to conditions different from the past, you introduce variability, but the downside is, for instance, the normality assumption. Markets have fat tails, extreme events more frequent than expected, so you could underestimate two risks. And then the alpha and beta parameters are somewhat arbitrary, I would say. And the coupling between prices and macro makes interpretation a bit harder. So, two approaches: faithful but rigid historical replication, and synthetic generation, exploratory but perhaps less realistic. Let's see how the model behaved in some scenarios from the presentation, comparing the two methods. Let's start with a positive scenario, replicating the 2012 till 2014 bull market. There's an interesting result with the historical replication. The model leans heavily on the healthcare ETF, that is the XLV. Healthcare, not technology. It seems wrong. And here's a key point. The model doesn't have a crystal ball. It reacts to the signals of that replicated historical moment. And as the article notes, during the period, the XLV ETF was doing very well, better than the other ETFs. So the choice was consistent with the model, with the data model was seeing. In the lower charts on the left, there are the ETF time series that mirror the period you want to mimic, so the 3 years, starting from today. While in the lower right charter, there are the ETF series of the same length as the period you want to simulate, but starting from today, going backward into the past. Back to the performance, over those 3 years, the portfolio has a 27.1 compound annual growth rate versus the benchmark with a 24.1%. Now let's use synthetic returns to simulate a 1-year bull market. So with synthetic returns, the allocation is similar. Still the healthcare sector, but it arrives a bit later. The price paths, however, are different, flatter, less explosive. You can also see that gold does well at the start in the simulation. This is something that did happen initially in 2012. Now let's change gears. The acid test. How did it react when simulating the COVID period from February to April 2020? With historical replication, the reaction was very defensive. Drastic reduction in equities and strong shift into gold. The results are notable. Portfolio with plus 64% of compound annual growth rate, Sharpe of 0.13, and drawdown around 12%. Over the same simulated period, the benchmark posted minus 5% and a drawdown over 33%. Here's the protection shows clearly. The reaction is not identical to what it would have been in the real 2020. Why? Because the starting point of the simulation is today. Let's say the test moment with a recent history and level of volatility and momentum different from pre-COVID 2020. The sequence of shocks is the same, but the initial context is different, and that influences the specific reaction. And here we are considering a 3-month window. Now let's look at synthetic returns simulating a 1-year crash. The allocation is similarly defensive, so gold, but the returns are very different, moderately positive, not the previous plus 63%. That's because a vanilla normal simulation struggles to replicate the violence and V-shape of the COVID crash. Then another crucial point is the duration. The historical replication lasts as long as the event, just a few months, 3 months. The synthetic simulation here lasted 1 year. This underscores that the two methods test different things. One tests coherence, the other parameter sensitivity. Let's see a few examples from the table. 1 year performance, historical replication. So the bull market from 2012 to 2014 replication, we have a portfolio with a compound annual growth rate of 2007% versus the S&P 500 of plus 24%. In the synthetic simulation, the delta between portfolio and benchmark is present, and there's a higher return per risk. In the COVID crash, the 2020 replication, the portfolio shows a plus 36% versus the S&P 500 of minus 4.9%. but also a drawdown of minus 12% versus the minus 33.7%. The synthetic simulation, instead, appears slightly in favor of the benchmark. Finally, we have the financial crisis scenario, where we get higher return and Sharpe ratio for a portfolio of simulations, although in the synthetic simulation we see a higher max drawdown. The picture that emerges from this table with historical replication look positive, I would say. The model shows a certain ability to adapt. It does better or protects more than the benchmark in almost all cases, especially the turbulent ones. Yes, this is the main conclusion of the analysis. Historical replication, despite its limit, is seen as more indicative for testing the strategy in realistic past scenarios. Both techniques, in any case, are useful to uncover issues and weaknesses before moving forward. Overall, the system's reaction was judged positively. So what are the main strengths that stand out from this presentation-based analysis? I would say mainly three. So first, good protection in crisis. Secondly, the ability to generate extra return even in sideways market without a clear direction, thanks to rotating among sectors. And third, it seems to use technical signals, macro indicators, to understand which market regime we are in and adapt the strategy. We are almost at the end of this video. The results show interesting capabilities, but also, as is normal, areas for improvement. So what are the key takeaway here? The takeaway, in my view, is the critical importance of stress testing and sensitivity analysis for these AI models in finance. You can't rely only on a backtest, no matter how nice it looks. Trust must be grounded in understanding, even if partial, given the black box nature of how the model might react to the unexpected, to shocks different from those already seen. And this brings to mind a final reflection, perhaps a bit provocative. These models learn from history. We test them by replaying the past or by varying known statistics. But what would happen with the truly unprecedented future events? Something that resembles no crisis, no rally, no volatility regime seen so far. How far could we trust? That's the point. How far could we trust decisions made by algorithms whose internal logic, in the end, despite all the tests, remain partially opaque? And an open question, I would say crucial for the future of AI in finance. But that's what we can do with a scientific paper proved methodology. Thank you for watching.